Hey everyone, in this video we're going to do another example of finding the derivative of our function using our limit definition, and we're going to use the limit as x approaches a definition. So here our function is the square root of x, and we just want to find kind of the general derivative at any point. Eventually we're going to talk about the derivative as its own function, and thinking about the derivative at a general point is helpful for that because now we can let our x value basically be anything. We can let it vary. So it'll be very nice if we want to find the derivative at a bunch of different locations. Don't have to go through the limit process every single time. If we want to find f prime of a, we have to compute the limit as x approaches a of f of x minus f of a over x minus a. All right, so to find our derivative using our limit definition, we have to first evaluate these pieces in that general formula. What is f of x and what is f of a? Well, f of x is just our function, the square root of x, and f of a is just the square root of a, our function evaluated at x equals a. So if we plug that in, our limit now looks like the limit as x approaches a of the square root of x minus the square root of a all over x minus a. And so we cannot evaluate our limit at the moment using direct substitution. If we try to just plug in x equals a, everything would kind of cancel out and we get 0 over 0, that thing we call an indeterminate form. In our previous examples where we tried to find or evaluate limits like this, it all came down to like canceling a factor like of x minus a. And we can do that here. One way to factor or cancel out the factor of x minus a is multiplying both the numerator and the denominator by the quantity called the conjugate. You probably learned about that when you were rationalizing roots in previous math classes. So we could do that here. Instead of multiplying by the conjugate is by factoring the denominator. It's actually a bit tricky, but technically the denominator is one of those difference of squares patterns. It's just not one that we have really seen too often. So we can think of x itself as the square root of x squared. Technically the square root of x squared is the absolute value of x, but we're going to kind of ignore that here. It all works out anyways. And similarly, we can think of a as just the square root of a squared. Now that might make it a little bit easier to see that that is the difference of squares. And we can always factor the difference of squares as that first thing minus the second thing after we've taken the square root, multiplied by that first thing plus that second thing after we've taken the square root. So this is the same thing as the limit as x approaches a of the numerator stays the same. It's the square root of x minus the square root of a. But now our denominator can be broken up as the square root of x minus the square root of a multiplied by the square root of x plus the square root of a. And if you're having a hard time following that we could factor the denominator like that, you can always go back and multiply by the conjugate, or just distribute that denominator, multiply it out, and make sure we get back to x minus a. All right, so at our current spot, we can see that there is a common factor that we can cancel out in the numerator and the denominator. It's the factor that causes the issue of 0 showing up in both that numerator and our denominator. So what would be left over after we cancel that common factor? Well, we still have our limit we haven't taken. Everything got canceled out of the numerator through division, so we have a factor of 1 left over. In our denominator, we have that quantity, the square root of x plus the square root of a left over. And so now we can try to use our direct substitution property. Just plug in x equals a, and what do we get? Well, we get 2 square roots of a in our denominator. So that's 1 over the square root of a plus the square root of a. Well, those are like terms. So we could write that as 1 over 2 times the square root of a. That is kind of the general derivative of our square root function at any point. So now we could quickly find the derivative at 1, 2, 3, any spot where our derivative is defined. We can find it using this kind of shortcut formula we've created.